In this weights equation, in every update we are subtracting the learning rate multiplied by the partial derivative. So why are we subtracting an amount from the value of this parameter w rather than adding, right? Because either ways you're making an adjustment. The reason is when our when our derivative is positive, this means that this function is growing at this point, right? That means your error is growing. That's when the derivative, your slope, will become positive. And what we want is, in that case, we want our derivative to decrease. So we want our function to go towards the left side of the x-axis, right? Because the rightmost point on the x-axis is the most positive. The leftmost point on the x-axis will be the 0 or the most negative point, smallest point, right? So we want to go towards the left side, right? We want to decrease our w value and for to get back to the lower error. So at that point, because this is positive, our positive derivative multiplied by our 0.01 whatever learning rate is always positive. So these two values will be subtracted from our w, and so the w value will decrease. So the moment our error starts increasing, our w value will start decreasing. And when our derivative is low, right, when it's negative, so our error is decreasing at this point. So when our error is decreasing and we are continuing and it's decreasing, that means we have to go ahead, right? We need to increase the value of w, right? In that case, this negative derivative, when subtracted from w, negative into negative minus minus becomes plus, so your weight will start increasing, and as your weight starts increasing, you will start approaching the global minimum, right? That is why we use that's why we are subtracting the partial derivative from our parameter value. Now here it is simply, he has coded the thing he has coded the entire gradient descent. Now firstly we defined an update w and b function. We are using the same spendings and sales example which we saw here, right? This chart that we saw here, this one. So we are using this data to create our gradient descent program in Python, right? So he's using spending, sales, our values w and b, and alpha here refers to this sign over here, which refers to the learning rate. So initially, of course, we are going to initialize this is our derivative, right? dl by dw, which simply means derivative of loss by derivative of weight. It will both be initialized to 0. N is simply the number of records, right? N always refers to the number of records. If you see here, sorry, give me a second. Yeah, here we are doing 1 divided by n to get average, right? To get the average, because n is the total number of records. So 1 divided by n will become the answer to this divided by n, right? So n is the total number of records. So we are setting our total number of records to the number of records that we have, obviously. Now for I in range n, so for every record in this range, we are calculating the derivative using the formula which we saw here previously. This is the formula for weight, right? So we are going to simply use this same formula, except that we're going to code it in Python. So for that, all we need to do is -2 into spendings into we open this bracket, sales minus weight into spendings plus b, and we do the same for derivative of bias. But in derivative of bias, we don't use spendings because we are only bias simply is your y-intercept. So when you're calculating intercept, you don't need the let me see. You don't need the y-axis, right? You only need the spendings axis because it will come over that point. Sorry, we need only the y-axis, right? X-axis will be 0, so unrequired. Y-intercept is simply what is your value of y when x is 0. So at this point, where is your line, right? So if your line starts from, for example, here, your intercept is around 2.5. So that's why you don't put your spendings here, you just directly put sales minus spendings plus intercept, right? You don't need this. Now you are creating your learning rate. So you're simply saying by how much do you want to update your weights and bias at every iteration. So here you're saying, okay, weight minus 1 upon float n. So simply it's 1 upon number of records into your derivative into alpha. We have still not declared alpha, it seems, but I think there is some constant value which is being used. So yeah, so we are uh, subtracting this amount, which is simply what we discussed back here, right? We want to subtract our weights by alpha into our partial derivative. So this is our partial derivative, right? Here is our alpha and this is our weight, right? Weight minus because want to we want average, right? We don't want it, we want average of the derivative, and we don't want, like, we are going to take an average for the derivative, because for every point I, you can see here, for every point I we are calculating a new derivative. So we are taking an average of the derivative, and that average will be multiplied to the alpha and subtracted from our weights and our bias. This is the function where we are simply creating a loop, right? So we are simply saying do this entire process, keep doing it again and again, right, until we get the lowest possible loss, and then we are printing our epoch number of epochs and your average loss. So this will be your result. Here you can see you have your epoch 0, then epoch 400, epoch 800. It's simply showing how your line is adjusting, your classifier adjusting over time, right? And here you can see this is the loss. So it's showing you at epoch 0 you had a 92 loss. At epoch 400 your loss was 33, and your epoch per epoch your loss keeps decreasing until it's reached 19 at epoch or iteration 2800. Our alpha value in this case we are using 0.001. Weights and bias are of course initially, we have initialized to 0, and if you go for 15,000 epochs, obviously it will keep decreasing the error over time. But yes, improvement will slowly start to, it will slow down, because there's only a maximum amount of improvement we can do. Now we are predicting our x, w and b values, and it will return by multiplying the weights value we have now found to be optimum into our x, which is what we will give the data, plus the b. So simply what this will do is, we can now give it a what do you call it, we can now give it the spendings that a company has spent on radio advertisements, and it can predict how much sales a company will make based on this graph. So if I said the spendings are around 30, it can tell you that okay, the sales are around 25, right, using this line. But this is not the right one, so it will use actually this one. So it will say, okay, for 30 it's not actually 25 as it may appear to a newcomer, it's actually around 15. So as you can see, we ask it to predict for 15,000, I think this is, which falls around here, right, and it predicts it to be 13. So let me see if you can have it closer. Here we are predicting for 15, which falls around here, and on this line it's coming to around 13, right? So it predicts 13.97. Now for gradient descent there's a problem, right? We had to run thousands of epochs to get to our correct value, and this is not even exactly a very big data set, right? So, and you cannot, so, and that mainly happened because your learning rate is very small. It's, what is our learning rate again? 0.001. It's a very small learning rate, and your machine, your model is taking a lot of time to make adjustments. However, you cannot keep a large learning rate either, or your model will make adjustments which are too big and will miss the global minima, which is the lowest point of error in its speed. So it will make, humongous adjustments and miss. For that we need to keep a small learning rate, and this is causing our machine to take a lot of time, and for large data sets it will be really slow. But there have been some significant improvements recently. First is mini batch stochastic gradient descent, or mini batch SGD, right? This speeds up the computation by, so it simply uses smaller batches of the data. So it doesn't take this whole data, it takes some amount of the data, small batches, and runs gradient descent on that to reach the perfect weights and bias, right? So yeah, there are many methods which are used to speed this up or improve gradient descent. There is SGD, there is ADAGRAD, momentum, RMS prop, but mainly RMS prop and ADAM are used. Gradient descent and its variants are not machine learning algorithms, right? They are just solvers. They just help us find the optimum values for the parameters in our model. They are not the actual algorithm themselves. So here we have coded how a basic machine learning algorithm works, right? How to code a very basic machine learning algorithm. So mostly you will be using this code with just different names for your model. See, so you're defining your training X and Y sets, okay? You are importing your model from your sklearn library in case of machine learning, right? For deep learning you have to import a library known as Keras, but we'll go into that later. Then you save your model, this linear regression model, you fit it on the data and save the result, which is simply the updated parameter model, into this variable model, and it returns that, right? After that you train this model again, right, and ask it to make a prediction for an x value 23, and then you print that prediction. So this is how you will basically, so simply you will import the model, save it in a variable, right? Feed it, fit it on our training set, ask it to make a prediction, and check it and test its accuracy. That is the basic way your machine learning model will work. You can replace the linear regression we use with any other model: logistic regression, support vector machine, decision tree classifier, or any other of the models which are included in scikit-learn, which is short form for sklearn is just short form for scikit-learn. Now, many learning algorithms have different parameters they use. SVM uses C, ID3 uses D, and entropy, right? So everyone has different. K-nearest neighbors will use distance, Euclidean distance, and others, right? Some algorithms accept categorical features like clustering. You cannot give clustering a numerical value and ask it to solve the problem, because that's not the way clustering works. Mainly, you can nowadays, you have k nearest neighbors which can do that, but initially that's not the way clustering worked, right? And some classification models like SVM, support vector machines, and KNN, k nearest neighbors, when you give it a feature vector, it will only output the prediction, which is like 13.97. Other models like logistic regression and decision trees will also return how confident they are based on their, based on the accuracy of their previous predictions, right? So this can be interpreted as their confidence, right? So you can know which prediction you can lean more on. There are some models like SVM and KNN which can be used for both classification and regression, while others can only solve one type of problem. Like linear regression can only solve a regression problem. It cannot work on a classification problem, because a person will either buy the insurance or not. But linear regression, as I explained before, spans from minus infinity to plus infinity, even if the only possibilities are 0 and 1, right? So it's not really good at solving classification problems, and so it is considered as a regression model.